Welcome, everyone. My name is Dawn Mullally, CPASS's Communication Manager, and we are delighted to have you attend the CPASS Discovery Seminar Series. CPASS scientists do everything from explore our ocean depths to fly into hurricanes, to our heliophysicists modeling coronal mass ejections, and those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR-UCAR community, and our many colleagues at universities and agencies across the globe. So just to orient you, we are using Slido, which is located below the presentation screen, so you can pose questions to our speaker at any time during the seminar, and they will be answered after the presentation. It is my sincere pleasure to introduce to you today's speaker, Ben Trabing, who is an associate scientist at CPASS, where he works in the Storm Surge Unit at NOAA's National Hurricane Center in Miami, Florida. His work at the National Hurricane Center began with conducting numerous forecast model verifications to evaluate and document the performance characteristics of track, intensity, and wind structure forecasts. He updated the HFIP, corrected consensus approach model, and developed a probabilistic product to improve forecast uncertainty surrounding hurricane landfalls. Today, Ben is actively working on expanding the capabilities of probabilistic storm surge modeling to U.S. Pacific Islands, as well as improving the representation of storm structure in models. Dr. Trabing joins us to share his recent work, our forecasts of the tropical cyclone radius of maximum wind Skillful. Ben?
All right, so I'm really excited to talk about some of the work we've been doing and trying to figure out whether or not forecasts of the tropical cyclone radius of maximum wind are actually skillful. I'd like to acknowledge that this work has not been done purely by myself. It's been a whole group project with a lot of different collaborators. A lot of this work has already been done by Andy Penny, Cody Fritz, as well as assists from Jonathan Martinez and pretty much the whole storm surge unit at the National Hurricane Center. I would also like to mention that if you want to get into the details of some of this, I'm not going to be able to have a whole lot of time to do that, but I'd encourage you to check out our paper that was just published in GRL last month. All right, so just again, kind of give you an outline of what I'm going to be talking about. I'm going to first get into some background of storm surge and why the radius of maximum wind is actually important for forecasting surge. I'm going to talk a little bit about the probabilistic storm surge model called P-surge that we use in operations at the Hurricane Center before diving into some of the observing challenges with the radius of maximum wind. Then go into kind of talking about the forecasting techniques and do kind of a comparison between the models to try and answer this question of whether or not these forecasts of the radius of maximum wind are actually skillful. So storm surge has historically been one of the leading killers associated with tropical cyclones. A report from Ed Rappaport back in 2014 showed that 49% of all the direct fatalities in the US associated with tropical cyclones were directly caused by the storm surge. Now, the National Hurricane Center recognized this, and the National Weather Service has started issuing watches and warnings actually since 2017. And since then, there's been a significant reduction in the number of fatalities associated with storm surge. So we know that these watches and warnings are working. Forecasting the storm surge is actually leading to kind of a reduced loss of life from these events. But of course, we're looking to get better. We're always looking to better communicate this information. And so this is kind of one of the motivations for why we're looking at the radius of maximum wind. If you're not familiar with what the radius of maximum wind really is, it's simply the distance between the center of the tropical cyclone and the location of the maximum winds. So we have the eye of the storm, which generally has very calm winds. Just radially outside of that is the eye wall of the storm. That's where the radius of maximum wind is found. That's where the maximum winds are located. Now, the radius of maximum wind is just one measure of the size of the tropical cyclone. There's also the radius of 34-knot winds, the radius of 64-knot winds, et cetera, that are actually used in operations. And those are all going to be important measures of the size that are going to kind of help us figure out where the surge is going to be. But that radius of maximum wind is really key in identifying where the maximum surge is going to go. There's, of course, other variables that are going to be playing a role in how much surge an event causes, such as the storm intensity, how fast it's moving, the angle of approach to the coastline, the bathymetry of the coastline itself. So all of these factors are going to be playing a role, and the RMW is one of these key factors. So the radius of maximum wind is a measure of size. And we could think about um, how the size impacts storm surge by kind of making this analogous to a wall of water. So if we have a area of winds, we can say that's basically a wall that's pushing water on shore. And this kind of animation from the Comet program really shows this nicely, where for the top here, we have a kind of a smaller storm, a smaller wall pushing water on shore towards this kind of hypothetical house. And when this is happening, a lot of the water can still escape kind of around it. It's not as much of that water is being driven onshore compared to on the bottom where we have a much larger wall. If we have a much broader wind field of the storm, it's able to push a lot more water and inundate this house here. We can actually look at this another way in terms of looking at our hydrodynamical models itself and just look at the sensitivity to actually changing the radius of maximum wind. So this yellow circle here is actually the radius of maximum wind, and we're keeping everything else really consistent. The intensity of the storm is the same. The position of the storm is the same. Everything else is the same. The only thing we're changing is the radius of maximum wind. And we can see that for this hypothetical case, what happens when we increase the size? If we look at, for instance, Sanibel Island here, when it's originally a small storm, we have kind of 5 feet of water above datum. Cape Coral is over towards 1, 2 feet over near Fort Myers. And then as we increase the size of the storm, we can see that how that water is being pushed further to the south along the coastline of Florida. And you can see how now these values for storm surge up to 15, 16 feet now in the Cape Coral area. So this is a much more significant event simply by changing the radius of maximum wind. We can also see that the location also gets maximized further to the south. And you can see that areas of Naples, Marco Island, all the way down the coast are now feeling kind of the brunt of the impacts from storm surge just by changing the size. So the size really does matter. So at the National Hurricane Center, we forecast the storm surge using the probabilistic storm surge model called P-surge. It's really just an ensemble of sea, lake, and overland surge from hurricane model runs. If you're not familiar with that model, it's pretty much what I showed in the previous slide. It's really computationally efficient and does a good job at modeling storm surge. But we create essentially an ensemble of tracks. For instance, as an example here on the right is for Hurricane Ian. We have all these different tracks centered around the official forecast from NHC. And we can account for the uncertainty within that track forecast and make sure that even though the storm kind of curves off to the right, we're still able to represent what is potentially going to happen from this event. So at the Hurricane Center, we use the official forecast. We use the errors from the National Hurricane Center's forecasts to get the uncertainty in the cross-track direction, the along-track direction, which is the speed of the storm and the intensity of the storm as well. So if NHC is forecasting a Category 2, we also have that sensitivity of looking at Category 3 hurricanes and Category 1 hurricanes to see how that changes the storm surge. The only estimate of the storm size, though, that we include right now is the radius of maximum wind, and that value is actually not coming from the official forecasts. The forecasts from the National Hurricane Center, they do the radius of 34, 50, and 64 knot winds, but not the radius of maximum wind. So we actually have to get that information from elsewhere. So I'm going to dive into kind of a little bit of a historical background here to really kind of illustrate and motivate this a little bit further. But in version 2.7 of P-surge, the radius of maximum wind was not forecasted. It was almost prescribed by other variables within the model. So it really had no idea of knowing what the radius of maximum wind should be for the individual cases. So this is just an example of the forecast in version 2.7 for Hurricane Laura in 2020. And you can see that for the 3 different members of the ensemble, it did a good job at about 48 hours onwards. But at the initial time period in the first 36 hours compared to the best track, it completely missed the size. It was way underestimating the size of the RMW, where we had on this case closer to about 15 nautical miles compared to observations, which shows that it was closer to about 100 nautical miles. That's a big difference. So in version 2.8, which became operational in 2020, instead now what we use is we know that observed value at the initial time period for the radius of maximum wind. So we can actually anchor the forecast to that. And so what P-surge did was now anchor the forecast to that initial value of 100 nautical miles. But after that, you can see that now we have the opposite problem, where now the forecasts of the radius of maximum wind are much too big out at 48 hours. And now we have a storm that's just unrealistically too big at pretty much all time periods. And this is really a problem anytime we have rapid changes in the radius of maximum wind. So in this time period for Hurricane Laura, it was rapidly intensifying. And generally, when a storm intensifies, the radius of maximum wind also contracts. So it completely missed that from this framework. So then in version 2.9, Andy Penning developed this multivariate linear regression technique that uses the variables that are in the official forecast to derive the radius of maximum wind and forecast it. So it uses the latitude, the intensity, the radius of 34, 15, 64 knot winds, fits those values to an RMW, and then we calculate the error distributions to use in PSurge based on the errors of that regression model. And you can see that in version 2.9, which became operational in 2021, now we're able to better represent how the radius of maximum wind changes with time, and pretty much at all time periods within this forecast, the best track value is within one of those different members of the radius of maximum wind at PSurge. Now, this is great. We've improved the representation of the radius of maximum wind. Now, how does that translate to improvements in storm surge? So this was work, again, done by Andy Penny, and I would encourage you to check out his 2023 paper, which really shows a lot more details about this. But we can analyze the performance of PSurge looking at the probability of storm surge exceeding 6 feet above NAVD 88 within a whole retrospective sample, and compare these with rock curves. So rock curves highlight the false alarm ratio on the x-axis with the probability of detection on the y-axis, where we really want to be on the top left of these different plots. And on the left is for version 2.7 with the simple derived radius of maximum wind within PSurge. And on the right is version 2.9, where we're actually explicitly forecasting the radius of maximum wind. And you can see that for some of these shorter timescales, the plot on the right definitely shows that these lines are definitely closer to the top left. And we can calculate kind of an integrated metric called the area under the curve for these to really get a better sense of comparing these values from previous versions to the new version. And if you're looking at, for instance, the 60-hour forecasts in version 2.9, our values for the area under the curve are now better than our 48-hour forecasts in the previous version. So not only have we improved the model, we've also improved the potential lead time and the performance of this model with longer forecasts. So now I'm going to kind of switch focus a little bit and talk a little bit about the observations of the tropical cyclone radius of maximum wind. And the reason I'm doing this is because observing the radius of maximum wind is a challenge. And that's one of the big reasons why a lot of this analysis hasn't been done before. Oftentimes, we only really have satellite imagery to actually identify what the radius of maximum wind actually is. So if we have this infrared brightness temperature loop of Hurricane Lydia on the right, this is from GOES 18 from last year. It was rapidly intensifying as it was approaching the Mexico coast. What is the radius of maximum wind from this case? And I encourage you to just kind of take a look and provide your best guess. You don't have to write it down, but think about it. What do you think the radius of maximum wind is going to be for the storm? There's no eye of the storm to really kind of anchor where the center is. There's also, you have to remember that the radius of maximum wind is a surface-based estimate, whereas GOES 18 is providing a look from the top of the atmosphere. So what do you think the radius of maximum wind is going to be? 10 nautical miles, 20, 30, 40, 50. And these circles I've drawn to scale to kind of help orient you. But without additional information here, it's really hard to know what the observed radius of maximum wind is. All right, so now I'm going to give you the answer. Really fortunately, we actually had a SAR overpass a few hours earlier. SAR is a synthetic aperture radar. It's a radar on board a polar orbiting satellite and provides really high fidelity look at the wind field of tropical cyclones. We don't get this information all the time, but when we do, it's absolutely fantastic. And so on the left here, you can see the wind field from the storm that was analyzed. You can see the eye of the storm with very calm winds, as well as the eye wall here with the very intense winds just really outside of that. You can see smaller areas of deeper convection, which have enhanced winds in it. So this information provides a really valuable look at the whole two-dimensional wind field of a storm. And what we can do is take this, look at radial cross sections, and really analyze where the radius of maximum wind is. And if you do that, we can pretty clearly identify the radius of maximum wind being around 9 to 10 nautical miles. So unless we have this, it's really hard to know. But we're getting more and more overpasses with this. And as we get a more robust data set of SAR imagery, we're actually going to be able to have more of a sample that we could actually potentially verify the two-dimensional wind fields of the entire tropical cyclones forecasts, which would be really good for future use of this. Now, another motivating feature here is that the radius of maximum wind is now being best tracked at the National Hurricane Center. So starting in 2021, the forecasters are going in, taking all the available observations of the radius of maximum wind, providing their best estimate of it, and these are essentially being quality controlled and included with the track, the intensity, as well as the other wind radii. So now we can be used for kind of a broad number of cases. And the National Hurricane Center specialists have even provided uncertainty bounds for when we should be more, when we should kind of analyze this data a little bit more and be a little bit more skeptical of what the radius of maximum wind is. And this is both a function of the observations we have, as well as the intensity of the storm itself. So for weaker systems, tropical storms, subtropical storms, where the center is going to be a little bit more ill-defined, knowing where the maximum winds is a little bit more unclear. That's where we're going to have enhanced uncertainty in the radius of maximum wind. As the storm gets stronger, category 1, category 2, we have a better idea of where the center is. There may not be an eye of the storm to know where the eye wall is, but once we get towards those category 3s through 5s, we know pretty well where the center of the storm is. There's usually an eye in the infrared and the visible imagery that we can use to pinpoint that center, and the RMW is a little bit more well-defined. So then also it's a function of what observations we have. Satellite observations only, a bit more uncertainty. Once we get scatterometer data or aircraft flying through the storm, that uncertainty is also going to be lower there. And anytime we have cases closer to land where we have next-red radars able to directly sample what's going on within the eye wall of the storm, those are also going to have cases with lower uncertainty. And that's something to keep in mind, that observational uncertainty is always there within these estimates of the radius of maximum wind. But I would also note that that uncertainty is also present in the track forecasts and the track centers within the best track, as well as the intensity as well. And those also have similar dependencies on the intensity of the storm. So again, getting into this now, a lot of motivation, but how good are forecasts of the radius of maximum wind? I've showed that the model that's going into P-surge and forecasting that radius of maximum wind has helped improve our forecasts of storm surge. Should we rely on that value in that forecast of the radius of maximum wind? Could we look at some of the dynamical or the regional models such as HAFS or HWRF, HMON? Would those actually provide better forecasts for this? We know that these models are able to kind of explicitly simulate things like eye wall replacement cycles and the inner core dynamics of the storm. So are those going to provide better estimates of the radius of maximum wind? This really hasn't been kind of answered before, so we really wanted to do that. And really answer the question of whether or not these models have any skill. And we're defining skill here as a relative to a climatology and persistence model. Basically, if we looked at just the climatological value, forecast that, are the models better than that? And so that's the first thing we actually had to do, was derive a climatological baseline to actually use to compare with the radius of maximum wind model from P-surge. We took advantage of a bunch of other studies have used kind of similar equations that have really derived this relationship between maximum winds with the intensity of the storm and the latitude. We did a little bit more of a power law relationship based on some of the work by Andy Penny, and found that that actual equation did a little bit better in terms of representing the data. But what we can do is basically take this equation here, plug it into the forecasts for the track and intensity from the other climatological and persistence model, and see how well that represents the distribution overall. And we see that when we do this for 72-hour forecasts, it actually does do a very good job at representing the peak of the observed distribution here. It's not going to capture all of those uncertainty and those larger values that we see for weaker systems that are a little bit more asymmetric, but it represents the peak of the distribution well enough to use as a climatological baseline. So then what we also have to do is we have to add in persistence, because it doesn't actually know anything about what we already know of the initial storm and RMW to be. So what we do is we take an offset between what that equation says and what was actually observed at the initial time period. We apply that at full at the initial time period. We linearly reduce it out to 60 hours afterwards, and that's now our climatology and persistence model. And you can see that if we now look at 36-hour forecasts where we've applied persistence into this, it better represents some of those larger values, particularly for weaker systems. Now, I should note that, again, the latitude and the intensity forecasts that are going into this are also from the other climatological and persistence model that's going and being used by NHC, which is OCD5. So overall, purely climatology and persistence going into this. One other thing to note here is that we don't actually have any other statistical guidance that we can compare with. So at NHC, we usually rely on the SHIPS or the LGEM model to predict the intensity of the storm from statistics, and those models don't actually forecast the radius of maximum wind. So we wanted to kind of have another statistical baseline to compare with to, again, provide a little bit more information of how well P-surge is actually handling these events. And so we can actually take advantage of a study by Dan Shavas and John Naff, and what they did was they used angular momentum principles and derived the radius of maximum wind using just the maximum winds, the latitude, and the radius of 34 knot winds. And all of those values are already in the official forecast from the National Hurricane Center. So really, we just had to plug and chug, and that's what we did. We also then applied kind of a similar offset technique because, again, this equation doesn't have any persistence in it, just to kind of anchor that forecast to what was actually observed at the initial time period. So now we have two statistical models. We have a climatology and persistence model. We now wanted to compare this with the regional models. And so there's two models that we're going to be comparing with, and that's going to be HAFS A and HAFS B. So HAFS is the Hurricane Analysis and Forecasting System model. There's two new models that are just going into operations. They went into operations last year. Upgrades just finished. I think they went into operations a couple weeks ago. But these two models are the next generation models. They're replacing HWRF and they're replacing HMON. And they've been shown to do a really good job at forecasting the track and the intensity of the storm, as well as the radius of 34 knot winds. So we think that the models are going to provide better good track and intensity forecasts. How well do they now do in forecasting the radius of maximum wind? And I would note that these models are overall very similar to each other. One of the main differences in kind of the configurations that I'm showing here is that the physics suite is different. So HAFS A and HAFS B has different microphysics, different boundary layer physics that's really going into it. And those are some of the main differences. All right, so now after all of that, which model does the best? So we're doing this in a homogeneous verification sense. So we're using 3 years of sample from 2020 to 2022. We're only using forecasts that were available. We're only verifying a forecast when it's available for all of the models. That's what I mean by when I say homogeneous. We're using standard National Hurricane Center verification rules. So we're not including any verifications of extratropical cyclones or any cyclones that had weakened and dissipated before the forecasts ended. And we're also not including any tropical depressions. Tropical depressions, of course, are going to be very ill-defined in terms of the center and the radius of maximum wind. And also the HAFS method actually requires a radius of 34 knot wind. So storms have to be stronger than that. And on the right here, what I'm showing is a plot where these solid lines are actually the mean absolute errors. These dashed lines are the biases. And then on the bottom is the actual skill relative to the climatology and persistence model for each of the different models. I'm going to be showing a bunch of different plots like this just to help kind of orient you. And the vertical lines here on the mean absolute errors are actually the standard errors. So you can get a sense of the variability within the forecast that actually went into this. What we can actually see just by jumping into the skill plot down at the bottom is that the forecast for the radius of maximum wind model that goes into P-surge, which is in magenta, are actually skillful out to 48 to 72 hours, which was good to see. The Shavasa NAF method actually was a little bit more degraded at the initial kind of time periods of the first 36 hours, but it was also statistically significantly skillful at 72 hours compared to the climatology and persistence model. And then the HAFS models actually lagged behind quite a bit. They were actually negative here, so they're actually not skillful relative to just using the simple climatology and persistence model, which was a bit surprising. We weren't really expecting this. I was expecting a little bit more competitive forecasts and actually be slightly better than the statistical models, but this really wasn't the case. So we wanted to dig into this a little bit more to kind of help understand what's going on. And so now it's the same plot as before, but now we're looking at, on the left, only tropical storms, so storms that were weaker than 60 knots. And then on the right is only hurricanes, so storms that were stronger than 65 knots. And we can see that it's really for these weaker systems where HAFS really struggles a lot. The RMW model that goes into P-surge is still skillful out at 48 hours, but it's kind of comparable with climatology and persistence after that, similar for the Shavasa NAF method. But for the HAFS models, that's where we get the biggest degradations in skill, where it's 30–40% less skillful than climatology and persistence for these weaker cases. When we jump towards these stronger cases, anything hurricane strength, HAFS is still kind of comparable with climatology and persistence. And you could say that HAFS A is a little bit better, but these are not statistically better if we actually run a test. Whereas the two statistical models, the Shavasa NAF method as well as the P-surge model, are both skillful at forecasting the radius of maximum wind for these more intense storms out at 72 hours. So to increase our kind of confidence in this and making sure that we actually are using the most reliable observations that we have, we did the same analysis by actually constraining our sample to only times where we actually have aircraft reconnaissance. So using that best track values plus or minus 2 hours from any aircraft observations of the radius of maximum wind, we can then do the same plot. And really, this is what kind of highlights and with more confidence that the radius of maximum wind model from P-surge is kind of the best model that we currently have at forecasting the radius of maximum wind, and it is skillful relative to climatology and persistence at almost all forecast time periods. I would note that none of the models were actually skillful out at 120 hours. So a little bit more work to be done that far out. But then even with this, the HAFS models are still not better than climatology and persistence at 20 to 30% less skill for the two different models. So One other thing that we needed to consider was that the radius of maximum wind and the intensity forecast are correlated. And so we know that because it's already in the equation for deriving the radius of maximum climatology persistence. So we did want to take a little bit more of a look at the intensity forecasts. We do the analysis, we can actually find that 20 to 30% of the variance explained in the radius of maximum wind errors is related to the intensity errors. And of course, those are going to be kind of reversible, whether or not the errors in the radius of maximum wind were related to the intensity or the intensity errors were related to the radius of maximum wind. It's hard to know exactly what caused what. But if we do this, we can actually do the same analysis and really ask the question of whether or not the intensity errors from halves played a role in this. For instance, for this case for Hurricane Lydia, it was rapidly intensifying. If the models didn't produce a forecast for rapid intensification and said, oh, it's just going to be a weaker system, we would expect the RMW errors to kind of coincide with that, having a more of a larger, broader storm within that. So the next thing we did was really just look at the intensity errors between the different models. And so these are the same plots as before, but instead of verifying the radius of maximum wind, we're now verifying the intensity of the storm. And again, broken up into weaker storms on the left and stronger storms on the right. And what we can see is that for the weaker storms, the two statistical models, which are using the official forecast from the National Hurricane Center, are actually outperforming the HAFS models. So you could say that there's a little bit of a bump in the better performance of the RMW forecasts, just related to better intensity forecasts there for the statistical models. But for the intense storms on the right, we can't necessarily say that. The forecast errors are actually very comparable for the sample. And even for storms that are kind of 96 hours, halves A and halves B were actually better at forecasting the intensity there compared to the statistical models. And I would also note here that all of these lines are above zero. So all of these forecasts for the intensity from halves A and halves B are actually better than the climatology and persistence model. So the climatology and persistence model, you can see it up on the top here, the mean absolute errors are much larger than the HAFS models. So we can't necessarily say that the intensity forecasts are the reason why there's larger RMW errors within HAFS models. So that's not really what's causing it. We can take a look at kind of an individual case really to kind of better highlight kind of what's going on here. On the left here is all the track forecasts from the official forecast from NHC in the magenta, which is going into P-surge. And all these greens are all the different forecasts from HAFS-B. You can see that overall they do a very good job at forecasting this track for Hurricane Laura. Really, after it kind of gets going here and this initial kind of westward jog of the storm, all of the official forecasts and the regional model forecasts are really lined up right on that center track. The model for HAFS-B does have a little bit of a westward bias, closer to the landfall in Louisiana. But other than that, track forecasts, spot on for the models. And if we look at the intensity forecasts, again, HAFS-B and the official forecasts were also right on the intensity forecast. The slow intensification as well as the rapid intensification was well forecast for Hurricane Laura. And so really looking at the track forecast, the intensity forecast, those really don't explain the errors in the radius of maximum wind. But if we do look at the radius of maximum wind forecast and compare those to the models, HAFS-B did actually a really good job of getting this increase in the storm size as it was kind of approaching the Caribbean islands. But when it's interacting with the Caribbean islands, that's where we get a lot of run-to-run variability and uncertainty in the radius of maximum winds from HAFS-B. And this makes it a little bit more difficult to use in terms of operations, but also trying to figure out what is actually going on there. And we've dug into this a little bit more, and part of this actually might be related to the vortex tracker that's going into the models. So trying to identify what that radius of maximum wind based on the model output itself could be playing a role here in kind of how it's actually defined and interacting with just various convective areas that kind of occur kind of along the topography and interact with the terrain and the islands here. So we're actually digging into this a little bit more in the future, but that's left for kind of future work at this point. So to summarize, storm surge is highly dependent on the tropical cyclone structure, including the radius of maximum wind. We've really shown that forecasting the radius of maximum wind is a challenge, but it can be done, even though we have these observational limitations. It's being quality controlled, it's being best tracked, so we have a more reliable data set that we can now use to verify the radius of maximum wind. We've created this climatology and persistence model for the radius of maximum wind and applied that to determine whether or not these models are actually skillful, and found that overall the statistical models that going into P-surge, as well as even just the Shrivastava method that we derived, are actually skillful at some time periods, P-surge being kind of up to 20% more skillful than climatology and persistence overall. But really the surprise here was when we kind of compare this with the HAFS models, that the HAFS models are not skillful relative to the simple climatology and persistence model. Now, to kind of conclude, we do need more guidance on tropical cyclone structure, both in terms of observations and forecasts. All of the models that we verified, all the statistical models we've essentially created on our own. We're looking at the different HAFS models. We're looking at, for instance, COAMS-TC is another regional model that we can verify. But that's pretty much it that we can actually use to identify what the radius of maximum wind is. And of course, better structure estimates of the storm is going to then lead to better estimates of the storm surge and better estimates of the risk for significant wind events, as well as rainfall estimates as well. So we need more observations, and we're hopeful that, for instance, more observations from SAR will be instrumental in actually helping to quality control and validate the models in the future. And I would note that when we're doing this analysis and looking at the RMW and with respect to halves, just because the radius of maximum wind forecasts in halves are not skillful doesn't mean that the other wind radii are also not skillful. And that's actually shown to be the opposite, where halves does actually have good forecasts of the radius of 34, 50, 64 knot winds. It's just struggling with the radius of maximum wind. And trying to dig into this a little bit more, whether or not it's directly coming from the model or the post-processing techniques going into the data. But we are hopeful that with the next generation of the HAFS models and then subsequent improvements, that more inner core data assimilation observations may go into constraining that inner core size of the storm, may actually also help lead to better performance of that model. We also need additional work here to quantify the role of track errors and eyewall replacement cycles, as well as the GFDL vortex trackers within those RMW errors. And that's some work that we're continuing on right now. And really, I just want to, again, emphasize that this is really a first step towards verifying the radius of maximum wind. It's such an important variable for just both the dynamics of the storm and for forecasting the hazards, which is really surprising that we haven't actually advanced this far and actually started forecasting the radius of maximum wind within any other techniques. So this is something that we think is important, that we really want to emphasize more for the community so that we can actually get more forecasts of this, better estimates of the radius of maximum wind, and actually the whole wind field of the storm in general for the future. So with that, if I have enough time, I'd be happy to take questions if there are any. And then if you do have any questions, feel free to reach out to me through email. Any feedback is welcome. Thank you.
Thank you so much, Ben. We truly appreciate it. So now we are in the Q&A portion of today's seminar, and I'd like to direct everyone's attention to the QR code on the screen. Please enter your questions for our speaker. And while you are doing that, I would invite you to watch to go to our webpage, cpaess.ucar.edu, discovery/seminars, for our upcoming seminars. The next one that is scheduled is for October 16th with Ann Christine Zinkin, who is a program specialist at NOAA's GOMO office. We also invite you to find this talk and other past talks on CPAESS's YouTube channel, so you can review it at any point in time. And it looks like we have a question here. How much R34, R50, and R64 forecasts themselves are skillful? For example, in case one wants to use them directly in an asymmetric model, and that's from NOAA. Thanks,
So
Ben.
I'm not sure if that's directed towards the HAFS models or if that's looking at the R34, 50, 64 forecasts from the official forecasts, or it's going into P-Surge. So if you could get some clarification there. But I know for the HAFS models, Andy Hazelton has done some work comparing the radius of 34 knot winds with HWRF and shown that it does do a better job at representing that. And in terms of the asymmetric components, I know there are some biases there, but I don't really know if it's how good it's going to do in those asymmetric cases. So that's something that we'll have to look at into a little bit more detail.
Okay, and then we have, what are the model improvements that you'll be working on next?
So there's a lot of different model improvements that are going into this related to the different basins themselves and kind of taking the P-Search model and exploring other areas. So one of the projects that I'm working on now is actually taking P-Surge, testing it and running it on places that don't currently have storm surge forecasts, being for Hawaii, for American Samoa, and Guam. So we're extending out the capabilities of forecasting in different areas. There's a lot of other different things that we're doing to look at kind of the bottom slip coefficients and making sure that the hydrodynamic models are doing the best they can. as well as also improving kind of the wave setup interactions within the model itself too.
How much? This is the one that we already received. Yes.
Mhm.
Yeah. So just to expand on that, in case Sarush wants to kind of clarify that question, what do you think are the biggest weaknesses that are important to be addressed first? If you know you had your druthers and a magic wand.
Ooh, well, so we're trying to also unify the wind field within the model from PSurge as well as the model that's going into the other projects and other products that are going out from the National Hurricane Center, such as the wind speed probability model. So one of the things that we're finding is that the P-surge model does good at actually identifying the radius of maximum wind, but it may not be the best for identifying the radius of 34 knot winds. So trying to make sure we have kind of the same wind field within both of these kind of modeling frameworks moving forward is going to be also probably one of the more important things that we can take a look at.
Okay. And then I believe I have a comment that is a clarification on the question that's on the screen. And it says, more specifically, I'm asking about values in OFCL advisory.
Okay, yes, the official forecasts of the radius of 34 through 64 knot winds are definitely skillful. As to what value of skill that is, not don't quote me because I don't necessarily know that, but I know that they are definitely skillful.
Okay. It looks like we have another question coming in here. Can you go into a bit of more detail as to the sensitivity of the surge forecasting to RMW? What types of things would you suggest to improve sensitivity to RMW in the surge context?
Okay, so surge is going to be sensitive to the radius of maximum wind. It's like I said, kind of showed at the beginning, it's kind of changing the size of the storm. So if you move the radius of maximum wind outwards, you're making the wind profile kind of larger as well. So I don't know if we can actually reduce the sensitivity to the radius of maximum wind as much without really knowing or without actually including a full two-dimensional wind field within to the model and kind of fitting it to other parameters. So the storm also has asymmetries. So with respect to motion, that's going to be impacting the radius of maximum wind and how sensitive things are. For instance, if you do have kind of a weaker storm with a little bit more of an asymmetric component to it, you could actually get kind of negative, actually almost no surge on one side compared to a significant surge event on the other. So in terms of improving the sensitivity of the RMW, I don't know if we can necessarily do that within P-surge. It's pretty much always going to be sensitive to that radius of maximum wind. Whether or not we know what that value is, so we can improve those error bars and lower the errors, that's another thing we could also do to kind of improve the forecast themselves.
Okay. I'll wait a little bit to see if someone has any more questions, but can you just make some general comments about this hurricane season? Seems like it's kicked off with some gusto.
Yeah, it definitely kicked off with the bang. East Pacific has been relatively quiet, which we would expect for going into a La Nina year. Atlantic has been pretty active to start, or we're getting a nice quiet period right now. Hurricane Beryl was definitely a monster. First, earliest Category 5 hurricane, earliest major hurricane kind of east of the Caribbean islands there. So uh, definitely going to be an active season. All the models and all the climatological forecasts are suggesting that it's going to be an active season. So just got to be prepared. It only takes one hurricane to cause significant impacts to places where you live, although we're pretty safe out in Colorado. So, but anyone else along the coastline should definitely be prepared for anything this year.
Yeah. Yeah. Well, thank you very much to you, Ben, and to all of your coworkers, especially at the Storm Surge Unit and at the National Hurricane Center. As you mentioned at the top of your talk, storm surge is one of the leading causes of death, and your work saves lives every day, and we really appreciate it. We appreciate all of your work. Um, I would like to thank everyone for coming to the UCAR.CPAESS Discovery Seminar and remind you to go to the website to find out about future talks at cpass.ucar.edu. And you will be able to find a link to this talk after it's uploaded on YouTube, typically within a week. Dr. Trabing, our sincere thanks to you for sharing your important work with us. Thank you also to Jesse Webb of UCAR Multimedia Services for his invaluable assistance. And I hope to see you all at our next Discovery Seminar. Good afternoon, everyone.